In this video, we'll explain photoelectric effect that will prove the corpuscular aspect of light, which is chapter 16 for LS and GS. Let us compare the wave aspect and corpuscular aspect of light. In wave aspect, different colors have different wavelength. Red color has longer wavelength. Blue color has shorter wavelength. While in corpuscular aspect, the blue color has more energy than the red color. The red photons has less energy. Blue photons has more energy. Of course, just we are representing different energies by different sizes of photons. Now if we have these two blue waves, as wave aspect of light, the first one has a low intensity or brightness, while the second has a high intensity or brightness. Since the brightness or intensity depends on the amplitude of the wave. While in corpuscular aspect of light, this is the first blue color and this is the second one. This is low intensity of brightness and this one high intensity of brightness. I have more photons in the second one. As we increase the brightness, the number of photons will increase. Hallwachs experiment. If we have a neutral or uncharged electroscope and we touch it by a negatively charged rod, it will become negatively charged and the needle will repel the stem, or the two leaves will repel each other. If we bring an ultraviolet light and focus it on the zinc plate, we observe that the deviation of the needle starts to decrease because some of the electrons are emitted from the zinc plate. Then it will collapse and no more deviation of the needle. But if we repeat the experiment and we touch the electroscope by a negatively charged rod, it will become negatively charged. If we bring a piece of glass that prevents the passage of the ultraviolet radiation, and again we bring the source of ultraviolet, but nothing will happen. No electrons are emitted, and the needle stays deviated. Now if we illuminate the zinc plate of the electroscope by an intensive red light, very high brightness that has a lot of photons, but nothing happened. But here it contradicts the wave aspect of light. Photoelectric effect is the emission of electrons from the surface of metal exposed to a convenient or suitable electromagnetic radiation. The electrons emitted is called photoelectrons. They called photoelectrons because they were emitted because they receive energy from a photon. Let us check what we mean by a convenient or suitable electromagnetic radiation. Here we have a cesium plate which is exposed to a red light of wavelength 630 nanometer, but no electrons are emitted. If we increase the brightness of the red light, more photons are coming. No electrons are emitted also. Let us shorten the wavelength, which means we increase the frequency. Still no electrons are emitted. Now we are observing electrons emitting from the cesium plate, and the wavelength is 580 nanometer, even if the brightness was decreased. We are still getting electrons emitted from the cesium. So the emitted electrons are independent of the brightness of the light, but they depend on the wavelength and the frequency of the photon. If we decrease more the wavelength, that means we increase the frequency. We can observe that the electrons emitted are very fast. They gain more energy. And if we increase the brightness, we can observe more photons are emitted, and at the same time more electrons are ejected. If I change cesium to copper, we observe that no electrons are emitted even for the wavelength 490 nanometer, while in cesium, electrons were emitted. So let us decrease the wavelength more. The wavelength is 380 nanometer. Now we reach to the ultraviolet color. The visible violet is 400 nanometer. Still we don't have electron ejected from the surface of the copper. Here 260 nanometer, still no electron ejected. 250 nanometer, we can observe that electrons are ejected from the surface of the copper. So we can notice that there is a threshold frequency and a threshold wavelength that each material has. So photoelectric effect will never take place unless we cross the threshold frequency and threshold wavelength. So the conditions to have photoelectric effect. A metal emits electrons if exposed to a radiation whose frequency is greater or equal to a certain value called threshold frequency nu0. That depends on the kind of metal. So the frequency of the radiation, nu, should be equal or greater than the threshold frequency of the metal, nu0.
Threshold frequency of a pure metal is the minimum frequency of the incident radiation which is capable of extracting electrons from the surface of this metal.
For each threshold frequency, nu0, corresponds a wavelength in vacuum called threshold wavelength lambda0, where lambda0 equal to c over nu0. Of course, we can recall that c equal to lambda frequency, always the speed equal to the wavelength times the frequency.
So a pure metal
Emits electrons if exposed to a radiation whose wavelength is smaller or equal to the threshold wavelength. As we said, the frequency and the wavelength are inversely proportional.
Threshold wavelength of a pure metal is the maximum wavelength of the incident radiation which is capable of extracting electrons from the surface of this metal.
Of course, each
Pure metal
has its own threshold frequency and threshold wavelength. The photoelectric emission is quasi-instantaneous.
A pure metal starts to emit electrons directly within 10 to the power minus 9 seconds.
When it is exposed to the convenient radiation, no matter what is its intensity. Let us explain this idea. Here you can observe whenever the photon reaches the cesium surface.
At the same instant, the electron starts to leave the plate.
Here you can see the copper plate. When the photon reaches the plate, electron is emitted. Thus, the energy of a radiation is quantized. What do we mean by quantized? It means that it can take only specific values that are multiples of a certain value called quanta. As Planck said, that depends on the wavelength or frequency of the radiation. So a radiation is composed of particles having no mass called photons. The energy of a photon is given by, we can represent it by W or E photon, equal to h nu. This is the energy of one photon. H nu. Nu is the frequency of this radiation, where h is the Planck's constant, as we said, and we can write instead of nu c over lambda. So E photon is hc over lambda. We can use both equations. And c is the speed of light in vacuum, 3 times 10 to the power 8 meter per second, and lambda is the wavelength. The extraction energy, or what we call work function.
If a metal is exposed to a radiation, an electron of the metal may receive only one photon.
If the energy of the photon is greater or equal to the extracting energy needed by the electron is emitted. If not, the electron remains inside the metal and keeps the acquired energy as heat or internal kinetic energy. So energy of the photon is h nu, or hc over lambda, should be greater or equal to the work function or the extracting energy needed by the electron. The work function is h nu0. Nu0 is the threshold frequency of this metal, or equal to hc over lambda 0, and lambda 0 is the threshold wavelength of this metal. Thus, work function or extracting energy of a metal is the minimum energy needed to extract an electron from the surface of this metal. We will use the electron volt as the unit of energy. So 1 electron volt is 1.6 times 10 to the power minus 19 joules. According to the wave theory, a metallic surface exposed to a radiation gains energy from the wave progressively and continuously. And no matter what is the value of the wavelength, the gained energy after a sufficient time should reach a value equal to the extracting energy of the metal, and the electrons should be emitted out of the metal. Let us check this experiment together. I have a copper plate here, and we will illuminate this copper plate by a red light of 400 terahertz and 750 nanometer wavelength. Here the brightness is 0%. I will turn it on, and this is 30%. Even if we wait, no electrons are emitted from the plate. As wave aspect of light, copper plate should gain energy from the electromagnetic radiation progressively and continuously, till the electron has enough energy to be extracted from the surface of the plate. But here, nothing happened. Let us increase the brightness more and more. As we increase the brightness, we are increasing the amplitude of the wave, so it has more energy, corresponding to the wave aspect of light. Even if I increase the brightness to 100%, thus I'm giving the plate more and more energy, continuously, even though the electron is not ejected. So wave aspect of light fails in this experiment. If I try to change the color to the green, nothing happened. To the blue, nothing happened. To the violet, also nothing happened. If we reach the ultraviolet, now we are getting electrons ejected from the plate. If I decrease the brightness, we can see that less electrons are ejected, but the speed of electron didn't change. Since the brightness depends on the number of photons, while the kinetic energy and the speed of the photoelectron ejected depend on the frequency of the radiation.
Again, the wave aspect of light fails in this experiment, while the corpuscular aspect of light is proven. The number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation.
Since as we increase the intensity or the brightness, we can see that the number of photons is increasing. And as the number of photons increases, the photoelectrons ejected will increase.
While the kinetic energy of the photoelectrons depends on the frequency of the incident radiation.
It is independent of the intensity. I have maximum brightness, but the speed of the photoelectrons not changing. While if I increase the frequency or I decrease the wavelength, we can observe that the speed of the photoelectrons is increasing. And as we decrease the wavelength more, we are getting more kinetic energy for the photoelectrons. I have one photon. The energy of one photon is h nu. But actually, if we have a light source, it will emit a lot of photons. So to calculate the total energy of this radiation, E total equal to n times E photon. Of course, n is the number of photons. So this is the total energy emitted by the light source.
But how much energy is received by the metal plate?
If I have a light source, of course we all know that light coming in all directions as spheres. And the area of the sphere is 4 pi r square. R is the distance from the source to the place of the plate. Total energy in 4 pi r square area of the sphere, and the area of the metal plate will give me the received energy. So energy received equal to E total times area of the plate over 4 pi r square. One incident photon may interact only with one electron. A photon of frequency nu hits the surface of a metal of work function or extraction energy W0. First case, if nu less than nu0, which is the threshold frequency, h nu less than h nu0. E photon is less than the work function of the metal. Thus the photon is reflected and the electron is not extracted. Case 2. If nu equal to nu0, that means h nu equal to h nu0, which is E photon equal to the W0 work function of the metal. Thus the photon is absorbed and the electron is extracted from the surface of the metal with zero speed. It will remain at the surface of the plate. Kinetic energy is zero. The third case, if nu is greater than nu 0. So h nu is greater than h nu 0, then E photon is greater than W0, the work function. Thus, the electron is ejected. Since the photon is absorbed, the electron is extracted from the surface of the metal with a specific speed, which is the kinetic energy of this electron. Einstein's formula. E photon equal to the work function plus kinetic energy. So the energy of the photon, if it is absorbed by the electron, it needs W0, the work function, to be extracted from the surface of the metal, and the rest of the energy will go kinetic energy for the electron. So instead of E photon, energy of the photon, hc over lambda, W0 is hc over lambda 0, and kinetic energy is half mv squared. Let us study the variation of the kinetic energy of the photoelectron versus the frequency of the photon.
I will take the kinetic energy along the vertical and the frequency nu along the horizontal.
So E photon equal to the work function W0 plus kinetic energy. I can write kinetic energy max equal to E photon minus W0. And instead of E photon, we can write h nu minus W0. So this is my equation, kinetic energy versus frequency. Nu 0 and W0. Nu 0 is the minimum frequency that is capable to extract electrons from the surface of the
Pure metal.
kinetic energy will be 0 since the electron is extracted from the surface of the metal without any kinetic energy. And this is the graph for metal 1, which has a threshold frequency nu 0 and a work function W0. We know here that h is the slope of the line, and also we know that h is constant, which is Planck's constant. So for any other metals, they will have their own threshold frequency and their own work function, but the graph will remain parallel. So the slope equal to h, which is Planck's constant. So all the graphs will be parallel, but different threshold frequencies and different work functions. Quantum efficiency. We know if the energy of a photon is greater than the work function of the metal, we mean E photon greater than W0, then this photon is absorbed and the electron is extracted, since this photon is capable to extract electron from the surface of the metal. But actually, most of these incident photons, whose energy is greater than the extraction energy of the metal, cannot cause a photoelectric emission. These photons are called ineffective photons. Effective photons, the photons which produce photoelectric emission. Ineffective is the number of effective photon, which is equal to the number of extracting electrons, which we call them photoelectrons. Then the photoelectrons equal to the number of effective photons. So quantum efficiency is the ratio of the number of the effective photons to the total number of the incident photon on the metal. So R equal N effective over the total number of photons, N. So let us try to understand this phenomenon using a nice example.
Those people are waiting for someone to rescue them from drowning after their ship sank. A rescue helicopter came and threw safety jackets for them. No men or women were rescued.
Because the safety jackets were for babies very small, so they are unable to extract men and women from the water.
Another rescue helicopter came and threw bigger safety jackets for them now.
This time the safety jackets were for men and women, and a lot of people were saved. At the next day, we observed a lot of safety jackets which are not used. These are ineffective jackets. For many reasons, no one was beside this jacket to use it. Actually, these jackets are effective and they can save people. No one used them to save his life. Because they didn't use them, they are ineffective. So these 6 jackets are ineffective jackets. Effective ones are those used by people. The number of effective jackets are equal to number of the rescued people. This man receive one jacket and there is another one in front of him. Can he wear two jackets together? He cannot. So one-to-one interaction. He cannot wear two jackets together.